Thank you again for joining us today. I'm going to turn it over to Alice, who's our payload systems engineer, who's going to be talking about the instrument science trades. Alice, the floor is yours.
Thanks, Michael. Good morning, everyone, or afternoon, wherever you may be. I appreciate you tuning in to our third day of our workshop. As Michael said, I'll be covering the instrument science trades. You've probably heard different pieces in Pontus's talk and Jim's talk and some of the topical groups lead talks yesterday that feed into this, but hopefully this will be a good overview to kind of tie all of that together. Next slide, please. I'd like to start off by taking a look at the instrument menu. This is something we've talked about in previous workshops, and this is one of the biggest outcomes of our study that we've performed, in that these are all the instruments we believe could contribute to science on an interstellar probe. So there's a wide range, and here we've captured rough estimates of mass and power numbers based off of heritage instruments that have been flown before or personal communication with scientists in the community that are developing instruments that could be relevant. In reality, whatever instruments are flown won't be chosen by us. They'll be chosen by a science technology definition team. And all of the instruments will have some, but we feel this list is relatively comprehensive of the types of instruments that could be flown. So I just wanted to emphasize this before delving into what we've done specifically in our study so that you remember there is a menu and there are choices. So if you could go to the next slide, to explain to you what we've done in our engineering study, we began with a mass constraint, which roughly translates to a power constraint as well, since the mass and power are often roughly 1-to-1 for a payload. So we set that at 90 kilograms. This is before contingency, and this isn't including spacecraft structures that don't contribute to the instrument. So for example, I'll cover a few spacecraft structures that are necessary for the instrument to be accommodated, but their mass isn't included in this 90 kilogram limit. For this study, we came up with two example model payloads. There's the baseline model payload, and that's heliophysics focused. That's the topic of this presentation. And once it's released, you'll see it's also the topic of section 4 in the mission concept report, along with the measurement requirements for a variety of instruments that can be included on that heliophysics focused payload. We also have the augmented payload. This has core heliophysics instrumentation, but also includes cameras for planetary science and astrophysics. That's going to be a topic of a talk I'm going to give in a few hours. And that's also a topic of Appendix A in the mission concept report. I also wanted to highlight that it was really the science traceability matrix that has driven the instrument choices we made in these example model payloads. So we paid very close attention to what's in that STM in order to choose which instruments should be in our payload within the constraint that we set of this 90 kilogram bucket. It is 100% true that a number of other combinations could be defended, but we had to pick one for the concept study. So this is what we came up with. If you go to the next slide, once again, to emphasize, what we did was to look at these measurement objectives and ask ourselves, what instruments do you need to be able to measure these effectively? Along with a bit of consideration to how long the instruments need to last in order to make these measurements, and what would be the best choice with regards to that. So Pontus has already covered this. I won't go into detail, but you can see that the science objectives leads to the questions, which lead to the measurement objectives, which lead to measurements from specific instruments. And once you have those specific instruments, this also leads to mission requirements in order to properly accommodate those instruments for them to be able to make the measurements they need to make. If you go to the next slide, The final mass and power for our baseline payload is 87.4 kilograms and 86.7 watts. Once again, you can see the mass and the power really do kind of track each other. So we came in just underneath the 90 kilogram constraint. And then I also have here marked a sense of what this payload covers. So the top bar covers the percentage of science questions addressed, where we went through and counted how many different measurement objectives are addressed by each type of instrument. So you can see for a heliophysics focused payload, it is appropriately almost 40% covered by charged particle measurements, 30% fields and waves, and then you have the complementary measurements coming from ENA imaging, dust, neutrals, and the Lyman alpha. The percentage of payload mass that each set of instruments takes up is similar, although slightly adjusted, but you can see that the percentage of payload mass does roughly track the number of measurements that each category makes. So if you go to the next slide, we have our final example baseline payload. So you can see here the bottom of the spacecraft, which is probably one of the best views to see how each of these different instruments accommodated. You have your magnetometer here on the bottom, which is shown stowed, which has 2 magnetometers. You have your plasma wave antennas, which extend far beyond what you see. You have your particle suite up here at the top, balanced out by the ENA at the bottom, which is next to the Lyman alpha spectrograph. And then you have your neutral mass spec and your interstellar dust analyzer here on the bottom to round out the payload. I have here reported the mass and power numbers that we've estimated for each one of these, which were derived from heritage instruments that we feel are roughly indicative of the types of capabilities that would be necessary, plus communications with the topical groups to adjust these numbers appropriately to accommodate certain adjustments to each instrument that might need to be made from what that heritage capability was. So I'm going to go ahead and go through each instrument and its accommodation. If you move to the next slide, we'll start with the fields. So we have the plasma waves, which are accounted for by 4 50-meter antennas, which are spin deployed shortly after separating from the 4th stage. And they're accommodated perpendicular to the spacecraft ram direction and 90 degrees apart from each other in order to capture 2 components of the electric field. The spacecraft spin rate is set to ensure that these antennas stay properly deployed throughout the remainder of the mission. It should be noted that deploying the antennas would require about 10 to 15 kilograms of propellant, and that the length and the types of wires is a science trade versus guidance, navigation, control, and propellant trade that will have to be made eventually. But this was the solution we came to, knowing that 50 meters should be able to accomplish pretty good science while still being short enough to not give GNC a complete heart attack. As part of our other part of the field suite, we have the magnetometers. So while both vector helium magnetometers and flux state magnetometers have good heritage, due to the lengthy duration of this mission, we felt that flux gates were more appropriate and might be more reliable. So we accommodated 2 flux gates on a 10-meter boom that's aligned with the spin axis of the spacecraft, which are spaced with the first approximately halfway between the spacecraft and the end of the boom, and the second approximately 2/3 down the boom, to capture the spacecraft generated magnetic fields accurately so that they can be subtracted from the measurements. And this boom deploys prior to the plasma wave antennas deploying shortly after separating from the 4th stage. Go to the next slide. We have our particles suite. So you can see that the particles suite, with the exception of the second cosmic ray telescope is accommodated out on a boom. And this is done in order to avoid field of view obstructions with the high gain antenna, which is 5 meters, very, very, very large. And you have 4 different main instruments here, which are capturing different energies and particles. So you have your plasma system here all the way on the right, which is capturing thermal ions and electrons up through the light pickup ions with energies in the 10s to 10,000s of eV. And then detecting energetic ions, electrons, and inner source pickup ions, you have the PUI instrument here in the middle. And then that would be in the range of roughly 10 to 1,000s of keV. And you also have your energetic particle system here on the left, which would be in a similar range. Your cosmic ray system here has a telescope on the top and then another on the bottom, pointing 90 degrees away from each other, which accounts for the highest energy particles, likely all the way up to 1,000 MeV. So these are, once again, accommodated on the boom to avoid a field of view obstructions in order to have almost full sky coverage, which is really important for the measurements. And then you have these 2 cosmic ray telescopes, which have a 90-degree angle between them, which is should be sufficient to measure the anisotropies expected in the cosmic ray detection. The pointing accuracy for each one of these instruments is assumed to be roughly 1 degree, while the pointing knowledge should be less than 10 degrees. If you go to the next slide, we have the dust and neutrals. Those are accommodated on the bottom. So we have the neutral mass spec here on the left and the interstellar dust analyzer on the right, which are co-boresighted with each other and accommodated on the bottom of the spacecraft. They are accommodated at a very specific angle of 38.5 degrees away from the spacecraft ram direction, which was optimized towards the inflow direction of dust and neutrals, which is assuming a flyout direction that takes us 45 degrees off the nose and remains near the ecliptic plane. This angle was also chosen to avoid field of view obstructions that would cause a glint with other instruments and spacecraft structures, such as the magnetometer boom. So depending on which direction you fly out, how you angled NMS and IDA would change. IDA has a 90-degree field of view and NMS has a 10-degree field of view with an antechamber that increases the acceptance cone to 90 degrees. And both of these instruments are assumed to have a pointing accuracy of approximately 1 degree, while IDA has a pointing knowledge of less than 1 degree and NMS has a pointing knowledge of less than 10 degrees. These instruments, it should be noted, they would also need to be covered when the thrusters are firing because you wouldn't want any of that to get in the instruments. Go to the next slide. We have our energetic neutral atom imaging, where you have these 2 fans accommodated on a boom that is opposite the particle sweep boom, which conveniently balances it out, but also allows for an almost entire sky coverage of the ENA measurements with a small sun exclusion zone of 10-degree half field of view. You need 2 instrument heads in order to achieve this angular coverage, and we're assuming an energy measurement range of roughly 1 to 100 keV. We only have this one ENA imager because the lower energy ENA imagers require heavy scanning platforms, since they're telescopes with small fields of view, to achieve the appropriate angular coverage, and the mass required by that was prohibitive, to say the least. But obviously, whoever makes these decisions in the future will make their own calls about exactly what energy ranges need to be covered. Lastly, right next to the ENA boom, we have the Lyman alpha spectrograph, and that's placed on the side of the spacecraft pointing away from the sun to achieve more than half sky coverage in the anti-sunward direction, achieved with an instantaneous field of view of 5 degrees that's able to capture roughly 140 degrees over the course of a month. We assume a pointing accuracy of 0.4 degrees for this instrument with a pointing knowledge of less than 2 degrees. This rounds out our payload. And we're pretty excited about all the pictures. I hope you enjoy the pretty pictures as much as our team does. And I'm happy to take any questions in the chat. And I believe we'll be headed to our next talk. Thank you.
Yeah, thanks, Alice. Thank you very much. So if you guys, if anybody online has questions for Alice, we've got about 10 minutes before the next talk, or 8 minutes now, I suppose. If not, we could declare a 5-minute break and let people take a breath for a few minutes before we move on to Elena's talk. But we can wait a minute and see if anybody's got questions that roll out from presentation of the payload layout. And we've got one. So Niben asks, as mentioned in the lecture, could you kindly let us know the telescope's operating bandwidth?
Niben,
so there's
could you clarify what you mean by operating bandwidth? Maybe just type another question.
Which range in the EMS?
Yeah, I see that. Which telescope are you referring to? Maybe it would be most appropriate to go to the example payloads. If you're able to go back in slides, it would be most appropriate to go to slides. Yeah, that'll do. So which one of these instruments are you referring to, Niben?
Because there are actually multiple apertures that you might call a telescope on a spacecraft. Well, for the CRS, he says. There we go.
So the CRS is meant to cover particles of ranges from about 1 to 1,000 MeV. Hopefully that answers your question.
All righty, and we have, thank you, Alice. And we have another question from Arno Wilders. Can you specify the total ionizing dose the instruments have to deal with and what RDM has been taking into account?
I think Jim would be better suited to answer this question as he was the one who handled the radiation analysis.
I could take that. Yeah, so we did do a radiation analysis of not only the Jupiter component, but also the rest of the trajectory, especially as we're going out for cosmic rays, particularly for the single event upset problem, single event effects problem. The total dose is not not too different from other missions that have been flown in this environment. And it depends a whole lot on the shielding. So instruments out on booms, for instance, may need to do some tailored shielding. But we think we can get it down within, the electronics that we can buy today that are hard to 100 to 300 kilorads without any problem. And that includes the usual RDMs of 2 and the margins on single event upsets and all those kinds of good things. So we have an environment defined, and it's in the concept study report for the mission if you want to get some more details of that.
It was curious to me, Jim, to see that the analysis came back with Jupiter still being the real highest sort of spot on the analysis. But the details of that will surely show up in our report in November. So thank you. And Niben also asks, Alice, could you clarify the difference between pointing knowledge and other pointing nomenclatures with respect to the field of view?
Sure. So pointing accuracy here means how well you know where you're exactly where you're pointing, and then the pointing knowledge is how well you know exactly where you're pointing.
it was a mystery to me, the balance between those two terms, until we started to get different instruments online on Messenger, where I realized things were pointed in directions where we thought they were pointed, and then there were directions that they were actually pointed in. And what was the difference between the two?
It's a very fine line and a difficult
Yeah.
tightrope to walk, for sure.
Yes, it is. Yes, it is. All righty. All righty. Thank you very much, Alice. Why don't we go ahead and take a 2-minute break here, and we'll come back in just a moment with Elena Provornikova and her presentation on the oops, I lost today's agenda. Where'd it go? Her presentation on trajectory and science traits. Thank you.